weld types. There are different types of weld: butt joint, T-joint, edge joint, lap joint, corner joint. And these are the type of joint. This is classification on the basis of the type of joint. We can also classify the on the basis of type of weld that is required for designer, what type of weld it is. So we have two types of weld that we'll be discussing in our course. This is fillet type weld. This workpiece is there, first and second, and this is all what exactly is the weld. And there are different terms here. This term from here to here, this distance or length is called weld, that is size of weld or weld leg, and the minimum distance from root of the weld is known as throat thickness. This particular portion which is additional from this triangular is reinforcement, and the throat thickness, actual throat thickness, is from here to here. If we connect or extend this line to the reinforcement, then it is actual throat thickness. This is face, uh, and we have another type of joint. This is another type of weld. This is groove weld. In groove weld, size of weld and the throat thickness both are same. It's used in butt joint, and the fillet weld is used in lap joint, T joint, etc. This particular portion or point is known as toe. This toe is not required in fatigue and impact load because it acts as stress concentration. We have to flush this surface or grind this surface to make the surface smooth. We have to remove this extra material if we have to use the welded joint for fatigue or for fatigue or impact load. The symbols plays important role for fillet weld as well as groove weld. First we will discuss what is the type of symbol, how the welded joint is designated. So this arrow represents the weld position. Then we have this horizontal line on both of this side. It represents on one side weld is there, on other side weld is there, and what type of weld it is, whether it is groove weld or fillet weld. We have symbol for each and everything. The surface finish is there, root opening is there in the case of groove weld. Number of spot and seam, they are in stud, plug, slot or projection weld. So here we write WPS, that is the welding process specification here between these two lines, that is tail. We can just for example we can use this symbol. It is the symbol for used for fillet weld. One is the weld size or weld leg or leg size. Then we can use this for convex contour, this for concave contour. Now this, when we have this triangle on the both side of the reference line, then it is the both side weld is there. Here this is intermittent weld, the weld is not continuous. This value, this is again weld leg. This is the length of weld for the first portion, and then this 4 is the second digit or second figure is representing the pitch of the intermittent weld. This symbol is again of good importance. We use this in practical situation as well, commonly used. All around weld, if weld is continuous starting from there and then as in circular, square or rectangular. This is on both sides with intermittent and staggered fillet weld. These are the examples that we have taken. If 5 is there, it means both side fillet, because the triangle they are on both sides with weld leg of 5 mm. This is intermittent. 60 200 means 60 is the length of weld and 200 is the pitch between two consecutive welds. So this is how this is defined. Intermittent staggered fillet. Then we have this another symbol, circle. It means it is all around weld is there. For groove weld, we have different type of designation, rather symbol on the reference line. This square weld, bevel groove, double bevel, V groove, double V. This is J groove, double J groove, U groove, and double U groove. So this is how we can designate a weld symbol for groove weld. This is the type of load that we can apply on a welded joint. For groove joint, for groove weld, we have this transverse load where this load is acting perpendicular to the weld plane. Here it is parallel. So under these two type of loading we will be designing this. Square weld, square butt joint or square groove weld is used when plate thickness is up to 5 mm. Otherwise, we have to prepare this as beveling of the plate. So single V groove. This is single V grooves. This is used for plates between 7.5 to 20 mm, and bevel angle is 60 mm for plate and 75 mm for pipe. And if plate thickness is more than 20 mm, we have to go for double V groove or double U groove. So now let us analyze the stresses acting, the stress analysis acting on the weld. Stress analysis is very simple in this case. We assume that failure takes place on a plane which is passing through the throat thickness where the resistance is minimum. So in this case, the normal stress will be there because load is acting transverse to this and normal to the plane of failure. So that is why this normal stress will be there, given by F divided by T by L, where T is equal to H in groove weld. So our design equation is maximum stress should be equal to design stress. So this design equation we can use. Another case is parallel load. In this case, the load is acting parallel to the plane along which failure takes place. So this is the plane where resistance is minimum. So in this case, shear stress will be induced, that is in plane shear stress, and we can calculate the shear stress like this, and design stress equation will become like this. Very simple cases. There is information which is available in manuals and catalogs and standards. Then from this table we can find out, we can take a proper appropriate value of design stress for mild steel electrode. We design any welded joint such that the strength of the weld, that is the load carrying capacity of the weld that we have deposited between two plates, should not be less than the load carrying capacity or strength of the member which you are connecting. So, and that all depends on the strength of the weld. So in the welded joint case, we can have efficiency of welded joint sometimes more than 100% if the weld that you are applying is having more strength as compared to the strength of the plate. From American Welding Society gives us a code that design stress can be taken as minimum of 0.3 times of ultimate tensile strength of the weld metal and 0.4 times of yield strength of the base metal. So this is how we can also, if we are given with ultimate strength or yield strength, we can find out the minimum of 0.3 SUT and 0.4 SYT to be used as design stress. Fillet weld, we have discussed about groove weld. Now we can discuss about fillet weld. Let us consider this example where load F is applied. We are connecting these two, plate number 1 and plate number 2, and this fillet weld is there. We have removed the reinforcement. This thickness along BD is throat thickness, the plate thickness is H, and the same is the weld leg. So in this case, if we go along the throat, this angle is 45 degree, but in practice or in actual condition, the failure does not take place along this, which is providing us minimum of the resistance, but somewhere else. So to analyze that, we have to take some angle, some simple any arbitrary position with which is making any arbitrary plane which is making angle theta with this BC, and let us try to analyze what are the stresses acting on the weld due to this theta. Then this distance BJ, here it is BD is T, it is the minimum distance, and this will be more than this, so let us say it is T dash, this no doubt H. If we connect this, it is this point K is obtained. The stress on this plane BJ will be some stress along the plane and normal to the plane. So let us designate this plane as normal stress, this plane as shear stress, and the sigma x was there because of this F. So now we can find out the state of stress at this point will be like this. So where if I take any small element around a point under consideration, then the state of stress on this element is given by this. So now let us try to analyze this, how the stresses are acting on the plane. I have reproduced the two figures. Then sigma x is given by F divided by H by L, because this is sigma x. The area which is resisting this is H into L. So here weld length may be L. Then sigma, that is the stress which is normal to this plane BJ, is F, here this sigma x into H, this is given by F. So component of this F along this is F cos theta, because this angle is theta, and due to this angle will also be theta, as this line is perpendicular to this line and this line is perpendicular to this line. So whatever is the angle between these two lines, the same will be angle between the two lines which are perpendicular to these two lines. So this is how we can get sigma, that F cos theta, and the sigma is F cos theta divided by T dash into L, and similarly this tau is there, which is F sin theta divided by T dash into L. So now we can plot this figure to connect T dash with T, and we can get this relation using triangle BCJ. If I use this triangle, I can find out that H, this value H, is given by T dash sin theta plus cos theta. We draw a perpendicular to this, and this H is this plus this. So here it is T dash cos theta and sin theta. So sigma, this expression now can be written as this expression, and this expression can be written as this expression. We have simply substituted for T dash to get sigma and tau. If I use maximum shear stress theory, then maximum, this tau will be maximum when theta, this tau by tau theta is 0. If we differentiate this equation and equate it to 0, I will get theta is 67.5 degree, and if I substitute back into this 67.5 degree, we get this tau maximum is 1.27, and so. And maximum distortion energy, if we calculate maximum distortion energy using this expression, and again differentiating this equation with respect to theta to get value of theta along which one Mises stress they are maximum. So we get theta as 62.5 degree, and we can substitute back into this equation to get value of one Mises maximum stress as 2.16 by HL. But the experimental results, we have just plotted this A, B, C fillet here, and then the experimental result shows that the variation of normal stress, this is the variation of normal stress and this is the variation of shear stress is quite complicated, and here is the variation of principal stress is on the basis of sigma and theta. So this variation means here the normal stress is 0 and then it is increasing to point B from this to point B, and likewise from point A to point B. So here the normal stress variation is this. The normal stress is acting at this point and it is at this point as well, and somewhere between this is changing nature from positive to negative, tensile to compressive. And shear stress variation, here it is maximum at B it is 0. If we go along this, the shear stress is 0 here, shear stress is 0 here. So this is how, this is the experiment, these are experimental results, and no whatever we have discussed in previous slide, that was analytical result, and as analytical result and experiment result, there is very difficult to make correlation between this two, so that is why we go for the easiest method and conservative one, that we assume that the failure is taking place along BD. So this gives us simple expression that F is that this shear stress is load divided by 0.577, which is the resistance over here. We assume that this load F is responsible for failure, not the component of F that we have discussed in slightly more complicated analytical method. So this gives us a fairly good result for designing the welded joint. So we assume that this load F is responsible for failure along BD, which is throat thickness, and we assume that this F is acting along throat thickness. So this is, with this assumption we design all fillet welds. So if there is double fillet, then this weld length will increase. It will be twice, or depending on the length of weld, we can add the add to this parameter L, that is length of weld, and this length is no doubt effective length, without considering considering that the starting and stopping behavior of weld, or this run over allowance, and what, there are different names for that. So these expressions are in case of the parallel weld. We have the same expression. We assume that this failure is taking place along the throat, and this is how we can find out the stress here. And again, the design equation is the same, that maximum stress should be equal to design stress. So this is maximum stress, and maximum stress we obtain using these expressions, and they are valid for other as well. So thank you for watching this video. We'll be discussing few more concepts of our welded joint eccentric loading in next video.